So today I'm going to show you how to find slope of a parametric. And like I said, you could have done those problems yesterday by converting, eliminating the parameter, creating your equation, then finding the slope of that. But that literally was not the point of those problems. That's why I took them out. Because today I want to show you how to find the derivative of a parametric. Because there is a formula. All right, and I'm going to derive it for you. You don't need to know the derivation. You just need to know how to use it. But I'm going to show it to you anyway, just because I think it's important to understand where it kind of comes from. Okay, so here is the derivative of a parametric. Okay, this is the formula that you're going to use. Right. So the derivative dy over dx is the same as the derivative dy over dt, dy to dt, over dx to dt, okay? And really simply stated, right, if I use keep, change, flip, this is where it comes from, right? Because this is dy over dt times, flip it, dt over dx. Well, those cross cancel and I get dy over dx. And so what's going to happen is you're going to be asked to find the derivative, but you're only going to have y in terms of t, x in terms of t. You don't have to eliminate the parameter. There's a way to just find the derivative from that, and that's the formula for it. And this is why it works. Again, you don't need to write this down if you don't want to. You do need to know this. It's pretty straightforward, right? It's in terms of lining up because, dy is on top, so you just find the derivative of y with respect to t. On bottom, you have dx, and that's the derivative of x with respect to t. That one's pretty straightforward. The second derivative is a little trickier in terms of why it works, but I'm going to show it to you anyway. Let's keep in mind the second derivative is the derivative of this. Agree with that? Okay, that's the sort of basis for what you're about to see. The derivative of this is the second derivative. So, again, this is the rule. Okay, it's the derivative with respect to t of what you found here over this denominator again. Okay, so think about it that way, if that helps. This bottom stays the same. That doesn't change. All you do is take that derivative of whatever this was, again, and put it over this. And then I'm going to show you where this comes from, why this works. You don't have to write it down if you don't want to. If you're very curious about why it works, then fine, you'll see. And you can write down as much as you want. But you could, in reality, I think it's just more important to pay attention to it so you can kind of see where it comes from. So let's start here. So, again, this is the second derivative. The derivative of the first derivative. This is this. Okay? Then what we're going to do is we're going to kind of rewrite this. So I could rewrite this as d over dt times dt over dx, right? Because these would cancel. These two things are equivalent. All right? And then nothing changed here. And here's where things start changing. Okay? This just goes to the bottom, and when it goes back to the bottom, it flips, right? We've already established that this is this, so this is the derivative of the derivative, and that's where that extra dx over dt comes from. Long story short, you have to know this, okay? So there's a little formula you got to memorize. This one's pretty easy. This one's a little trickier, but it does require you to find this first, okay? Which makes sense. I mean, if we're finding the second derivative, we need to have the first derivative. And why we're going to use that, this is going to give us the slope. This is going to tell us about concavity. And you're going to be asked to do that. And so in the problems that I took out yesterday, you were supposed to be writing equations of tangent lines. Well, in order to write equations of tangent lines, you need the slope, which means you need to know how to do this in the context of parametrics. So that's why I took those problems out. All right, let's do some examples. So here's a perfect example. Find the slope and concavity of a parametric. X equals the square root of t, and y equals 1/4 t squared minus 1. t has to be greater than or equal to 0 at the point 2, 3. Okay, so we're kind of envisioning a tangent line at that point if we knew what the graph of that parametric looked like, but we don't really have to do that for this particular problem. Okay. We don't have to eliminate the parameter. Now that we have those formulas, we can use that to our advantage. So again, when we're talking about slope, we're talking about the first derivative. When we're talking about concavity, we're talking about the second derivative. Okay. So this problem really boils down to you're going to find the first derivative and the second derivative. But it happens to be at that specific point 2, 3. And what we need to know is what t is at that point. And if we know what t is at that point, then we can actually find the derivative and the second derivative. Okay, so here's how this is going to go. First off, we're going to find the first derivative. Okay, and right off the bat, we should be thinking of this as t to the 1/2. Right, and so the first derivative means I have to take the derivative of this y on top over the derivative of this x, and we're taking the derivative with respect to t. Okay, so go ahead and do that. Go ahead and find the first derivative of dy or dx, knowing that it's dy over dt over dx over dt. I would also say you want to show your work and keep your work, but also simplify because we're going to have to figure out what the slope actually is. But the work is important because we're going to use that to find the second derivative. Because we copy dx over dt, and then we take the derivative of dy over dt. What is, since the y goes on top, what is the derivative of this with respect to t? 1/2 t, right? The 1 drops out, 1/2 t. What is the derivative of t to the 1/2? 1/2 t to the negative 1/2. So I start off this way, okay? And you're going to want to have that amount of work because when we find the second derivative, we're going to need to take the derivative of this and then we're going to copy this. But to find the actual slope, which is dy over dx, I should probably simplify this to try to figure out what my t equals. Okay. Let's simplify this because it'll make it easier to find our slope. So obviously the 1/2s cancel. What about this t over t to the minus 1/2? What does that end up being? 2 to the 3/2. Okay. This is helpful because now we can, now we'll be able to figure out what the actual slope is. The issue here is they're giving us a point 2, 3. We have to know what t is at that point. Okay. You can use either x or y. Which one do you think will probably be easier to use here? Yeah, this one seems a little less complicated. So what they're saying is if x is 2, what does t have to be? 4, because the square root of 4 is 2. All right, so that's really what we have to figure out. What is t at 2, 3? And once we know that, we can figure out what the slope is. And so, like we just said, it is 4. It works over here too. I think it's plus or minus 4, but that's when you have a situation like that, you just want to double check. Oh no, it can't be minus because t has to be greater than or equal to 0. So that takes care of that. Okay. So then what's the slope? Eight? No, 8? Are you sure? 8? So if I plug 4 in here, yeah, the square root of 4 is 2, cubed is 8. So therefore, the slope is 8 at 2, 3. Okay? Do you have to write it all out like that? I don't know. I would want to be clear if this is a problem on the AP exam. That way it's very obvious what you're stating and what you're doing. Okay? So that's the first part. The second part is determining concavity, which requires us to find the second derivative. Well, the second derivative is the derivative of this divided by dx over dt. Okay? So I would use this because it's easier than trying to find the derivative of all this by itself. Okay? So what I have here is, again, I just copy this over because it's the dx over dt, it's the same thing. And then the derivative of this is 3/2 times t to the 1/2. Okay? So you take the derivative of the derivative, that goes on top. And the denominator gets copied over. Then we want to simplify this and find out, is this positive or negative? Because if it's positive, then it's concave up. If it's negative, then it's concave down. Okay. So let's simplify this down a little bit. What is it when I simplify that all out? I'm just giving other people time to process.
3t.
It is 3t. Okay. So what is 3t for this problem at the point 23? 12. Okay. So at 2,3, the second derivative equals 12. Because again, t at the point 23 is 4. So therefore, is this concave up or concave down? Up. Positive. Okay. So when you have problems like that, that's what you're supposed to do. Okay. Just practice finding derivatives of parametrics. Moving on. All right, so here's an example of the kind of problem that I didn't have you do yesterday, which is my bad again. I apologize for that. Here's an example, okay? When we're writing tangent lines, writing equations for tangent lines, we're talking about slope. We need the slope. All right. And in a lot of your problems also, they're going to ask for horizontal tangent lines or vertical tangent lines, which means for a horizontal tangent line, we're talking about when the slope is 0, so the numerator is 0. So for a horizontal slope, all we need to know is dy over dt. We want to know when that equals 0. For a vertical tangent, talking about an undefined situation where dx over dt equals 0. So just know that those two special cases will come up in your homework. But again, horizontal tangent, slope is 0, which makes the numerator equal to 0. So that's dy over dt. For a vertical tangent, that means it's undefined, which means the denominator is 0, so dx over dt equals 0. And then we'll have problems like this as well. Okay? The key thing here that they're telling us, we want to know what the tangent line is when t equals 1. Instead of giving us a point like the last problem on x and y, they gave us t this time. All right. So we do need to know what x and y is at time 1, at t equals 1, because that's the point. Because we're still talking about point slope here. When we say use find a tangent line, we're saying point slope formula. I need a point and a slope, and I can write the tangent line. So we have to know what the point is, which means I have to know what x and y equal when t equals 1. So figure that out, please. What is x and y? 0 and 2. Okay, so when t equals 1, x equals 0, y equals 2, all we need to do is find the first derivative of this parametric, and we are done, basically. Okay, so go ahead and find the derivative, dy over dx. And actually, you could probably finish it. You have enough information for there to finish it. So, the derivative of this, again, I would right away make this t to the -1. That'll make finding the derivative of that easier. And here's what you should have gotten. Okay. Did you all get that? So then it's just a matter of figuring out what that slope is, right? So at time 1, what is the actual slope? -1. Okay. So that's another way of writing it. I know you've done this before with integrals, but you can do it this way as well. When you're evaluating a particular derivative at a specific t, that equals -1. So I have everything. I have my slope, I have my point, plug it in, there's your tangent line. Okay. And you can leave it like that. You don't have to, obviously you don't have to do the x minus 0, but if x was some other number, you would want to have it like that. The next topic in this, it seems unrelated, but you put it in here, so I'm going to cover it, is arc length. And these are calculator problems because it's going to require an ugly integral, and so you're going to show the setup, and then you're going to do the rest in your calculator. Okay. This originally gets covered in this workbook in chapter 8, and so I'm going to show you the original arc length formula. And when we get back to chapter 8, we'll talk more about this and where this comes from. But that is the original arc length formula before we knew anything about parametrics. Okay, so it's an integral from a to b of the square root of 1 plus the derivative of x squared dx. And when we go back to chapter 8, I'll show you where this comes from. But it's really not that important now. But other than the idea that we're going to essentially change the way this looks and put it more into parametric form, okay? And so for now, this is what you need to do. This is what you need to know. If a curve is smooth and does not intersect itself, then the arc length for parametrics is as follows. Again, so we've got our dx over dt, dy over dt. Those keep. I think that's why it's related to this, because this is our first go of looking at the derivative of a parametric, and so the parts of that derivative are in play for this formula. It's a pretty straightforward formula, and it has a lot of similarities to other things we've done, particularly to x squared plus y squared.
It looks like what does it look like? Something like a distance formula or the midpoint?
Yeah. There's definitely a relationship there. More like the distance formula for sure. It's not going to go away because on the next page I put it for our example. So there it is. I just put it again on the top because you want to use it as a reference. It's the same. There's nothing. You don't have to write it twice. But this is example 7, and so the key thing here is you're going to use example 6 that we just used, and so we know what dy over dt is. We know what dx over dt is. All right. And normally in a problem you'd have to do that again, but just to save us some time, I used that example, and he used that example that way, so it just we get practice at doing the setup and then punching it in the calculator. Okay. So just as a reminder, again, you have this in your notes, we have dy over dx was negative t to the negative 2 over 1. And the reason that we write the 1 down is because this is dx over dt, this is dy over dt, and they have to go in these spots. And then what's our a and b going to be? What's a? And b? 3. So our set is pretty straightforward, okay? We just plug all that into the calculator, and you'll get a number, so go ahead and do that. So yeah, either of those would be acceptable on the AP exam. Truncated, rounded. Again, I'm learning more and more about the idea that they're testing you for calculus, not the simple arithmetic. Okay, so that's why it's like, this is fine or this is fine. Okay? Questions?